Good afternoon. It's a great pleasure always to be in Iceland again. I've had the luck to have been here already a few times now, and I have to say, as a visitor, I can even enjoy the bad weather here, given that I don't have to live here all the time. I want to talk today about one of the consequences of global warming, and that is sea level rise, and give you a bit of an overview over the science of sea level rise. And I will start by a look in the past in Earth history. What you can see here is a model simulation that we did a few years ago of ice age climates, whole glacial cycles, and you see the last 200,000 years of the simulation running, going through two of these major glacial cycles. We were just now in the Eemian interglacial there, where only Greenland had a big ice sheet, but now we're moving into the last ice age, and the continental ice cover is expanding. And basically that follows the rhythms of the Earth orbital cycles that are the cause of these ice ages, as you have hopefully all learned in school. At least when I was in high school, that was part of the curriculum. And we simulate these past glacial cycles, of course, first of all, to understand how they worked, but also to test our climate models. And it's quite nice that they can actually reproduce these glacial cycles. Now, why do I show this in a lecture on sea level? It's because these huge changes in the ice cover on the continents had a really big impact on sea levels. And you can see that if you look at the the middle of the red curves, that's a sea level curve going through the last 120,000 years. And the scale for that is on the right. And you can see that at about 20,000 years before present, at the height of the last ice age, global sea level was actually about 120 meters lower than today. So this is the magnitude of sea level changes between the glacial times and the interglacials. And of course, at the end of the last ice age, going into the Holocene, sea level rose by 120 meters. That's the kind of thing we have to keep in mind when we are looking at what is happening to sea level now and how we expect sea level to respond to further global warming. By the way, just to mention it briefly, the red curves are from a model simulation driven only by these these orbital cycles, the forcing shown in the top panel there, and the black curves are reconstructed paleoclimatic data. Now, there's also been naturally warmer periods in Earth history, and the most recent one was 125,000 years ago, the Eemian interglacial, and this is from a review article that summarizes a lot of paleoclimate research and was published last year, and it shows how much higher sea level was in these past warm periods as compared to today, and how much warmer they were. And we find that in the Eemian interglacial, sea level was between 6 and 9 meters higher than today, even though global temperature was very similar. It wasn't significantly higher than it is now. It was about 1 degree above the pre-industrial. If we go back further in Earth history, 400,000 years back, third column from the left there, temperatures were about 1 degree warmer than presently, and sea levels were between 6 and 13 meters higher. If we go back even further to the Pliocene, then there is a lot of uncertainty, but it's at least 6 meters, and the upper level of that is debated. It could be 30, it could be 40 meters higher than the present. And so past warm periods have always come with many meters of higher sea level than what we have now. This dependency of sea level on temperature in Earth history has been illustrated in this diagram, where on the horizontal axis you see the global average temperature, and on the vertical axis the sea level relative to the present. And you can see that the dot in the bottom left, the last glacial maximum, was about 5 or 6 degrees colder than today in global average, but 120 meters lower sea level. Pliocene that I just mentioned, on best estimate, is around about 25 meters higher sea level and maybe 1 or 2 degrees warmer. And if we go back even further, 40 million years ago to the Eocene, that was the last time when the Earth was virtually ice-free on the continents, and we had 60 or 70 meters higher sea levels then. Now, if you compare this to the projections of the Intergovernmental Panel on Climate Change for the end of this century, about 3 degrees warming and 1 meter sea level rise, you see that is very, very low. And the reason why it is very low is that this is only going to be the beginning of a much larger sea level rise that will continue for many centuries, if not millennia, to come. That's because sea level is a slowly responding component of the climate system, and I will come back to this issue later on. Let's look at what is happening now. We've come out of the Ice Age. This is a reconstruction of global temperatures since the last glacial maximum 20,000 years ago. We've gone into the Holocene. We have seen the so-called Holocene optimum. Since then, the last 5,000 years, a very slight gentle cooling trend, which we have essentially turned around a bit more than 100 years ago. And the warming in the last 100 years has outdone about 5,000 years of cooling. And you can argue whether we're already warmer than the middle of the Holocene or not quite yet, but that's really not a very relevant point. What is clear is that no matter whether we get 2 or 3 or 4 degrees warming in this century, we will be catapulting ourselves way out of the Holocene, and that is basically the entire history of human civilization. Now, what effect is this modern warming having on sea level? For the last bit more than 20 years now, we have satellite observations that have a pretty good global coverage, and they show a steady rise in the global sea level around about 3 millimeters per year. As you can see in this graph, you can always download the current diagram here from that University of Colorado website. So it's easy to always see the latest what sea level is doing. What are the reasons for this modern sea level rise in the satellite era? There are different components there that can be individually attributed, and thermal expansion of the seawater contributes about 40% of that rise of 3 millimeters per year. That is simply the fact that water expands when it is heated up, and the surface oceans are, of course, getting warmer, and that is one reason why sea level is going up. A second reason is the continental ice that melts, and therefore additional water enters the global ocean. You can divide that up into the smaller glaciers that contribute about 30% of the rise currently, and the 2 big ice sheets on Greenland and Antarctica that contribute together about 20%, and roughly equal contributions there. And then there is a contribution from pumping groundwater used for agriculture from the land, which also, of course, mostly then ends up in the sea eventually, and is also a component of sea level rise. Now, the mix of these different components depends which time period you're looking at, and initially, for example, the mountain glaciers contribute quite a large amount because they are small, they're in relatively warm regions and are vulnerable, whereas in the longer run, the big ice sheets are taking an increasing share. We're already seeing the accelerated loss of continental ice from those ice sheets, and towards the end of this presentation, I will come back to this point. Now, if we step a little bit back and look at a longer time period, we know what sea level has done since the late 19th century from tide gauges, and these are several different compilations of tide gauge data. It's not so easy to combine them into a global average sea level signal because the number of tide gauges decreases the further back in time we go. And that's why the uncertainty increases the further back in time we go here. And also these tide gauges, of course, are not spread evenly anywhere in the ocean, but they are just along the coastlines of where there's land. And so that's why it's not, it's not without uncertainty to combine them into a global average sea level. But no matter how you look at it, it is very clear that we have this increase, and the data also tend to show over the 20th century some acceleration of the sea level rise. This rise is not uniform, by the way. You might perhaps think naively of your bathtub, and when you add some water there, the level goes up everywhere by the same amount. But there are some complicating factors on our Earth, of course, so that the sea level change is not the same everywhere. For example, if you look at this chart, the map here, it shows the sea level increase since 1950. And there are even some parts in the Pacific Ocean where sea level has gone down in this period, whereas on the opposite side, the western side of the Pacific Ocean, near Manila, for example, there, sea level has gone up disproportionately. In that particular case, this pattern between the eastern and the western side of the tropical Pacific is most likely due to an increase in the trade winds, which is well documented. Trade winds have increased significantly during this time span, and the trade winds basically blow over the water more to the western Pacific. And the individual little pictures show tide gauge charts from various stations there, with the red line being the global average and the gray lines being the individual tide gauges. An additional factor that I can mention at this point is, of course, that the sea level relative to the land doesn't only depend on how the actual water level changes, but also on the changes in the altitude of the land. In some areas, land is rising. In other areas, land is sinking. And for example, that's the reason why in Stockholm, sea level has gone down quite a bit relative to the city, because the city is actually rising after having been relieved, this region, from the big ice sheet that covered it in the last ice age. And this so-called glacial isostatic adjustment, so the response to the weight of the ice, that goes on for tens of thousands of years, so that now even 10,000 years after the end of the ice age, Scandinavia is still experiencing significant uplift of the land, and therefore is kind of lucky when it comes to the problem of sea level rise, because those areas will be largely spared in this coming century. Now, if we want to reconstruct sea levels even further back in time than we have tide gauge data, we can use various proxy data. And for the last millennia, it is very good you can get good quality data from salt marshes by drilling cores there into the peat, basically, and analyzing the layers that have been laid down over the last millennia. And here show some pictures of field work that we did together with American colleagues on the Outer Banks of Carolina. And recently, a whole lot of these results of salt marsh drillings have been compiled into a global analysis of global sea level change, the first of its kind, that was published in the Proceedings of the National Academy earlier this year. And it shows here on this diagram how much sea level has changed in each century since the beginning of the Common Era. And you see in some centuries sea level has gone up a few centimeters, and other it has dropped by a few centimeters. But the 20th century is the only one that shows such a large increase. And of course that is quite logical, because we have seen the strong global warming in the 20th century, and sea level rise is a logical, simple physical consequence of global warming because of the thermal expansion and the melting of land ice in response to warming. Now let's look at the future. We turn to the Intergovernmental Panel of Climate Change there, who does projections of future sea level rise based on the scenarios of future warming, and then running models for the glaciers, for the ice sheets, for the oceans, and combining all these factors to estimate how much sea level rise to expect. And the future, of course, depends on our emissions, because our emissions dominate climate change, and therefore it's shown for different emission scenarios. A high emission scenario is the red one, and a low emission scenario that would actually correspond to a successful Paris Agreement, namely limiting global warming to below 2 degrees. That would be that blue scenario. And you can see that the future sea level rise by the end of the century differs by about a factor of 2, depending on these emission scenarios. But that is actually, they're surprisingly close together, these two curves for sea level. If you compared the same scenarios for temperature, they would be very far apart. And the reason here is, again, what I mentioned already earlier, that sea level is a very slow responding component to warming. So that the good side of that is that it's only slowly starting, and we haven't seen more sea level rise yet because it's such a slow responding component. But the negative side is that it also doesn't respond very well to stopping global warming, to reducing our emissions. And in that blue scenario, you can see that sea level rise pretty well continues at a similar pace, or actually a bit faster than in the past, even though in that blue scenario, global warming is stopped below 2 degrees. So at the end of that diagram before 2100, global warming has long been stopped. Sea level continues to rise. The main thing that we can achieve by limiting global warming to 2 degrees is that sea level doesn't rise faster and faster. What we can achieve is that it keeps rising at the current pace, basically. So that is kind of the downside of sea level being such a slow responding component. Incidentally, that sea level rise predicted now by the Intergovernmental Panel on Climate Change in its last report is about 60% higher than in the previous report. That is another area where the projections by the IPCC in fact have been overtaken by the observed sea level rise that we already have, and they were probably too conservative, and the IPCC has recognized that and increased those. Although we did, around the time that the fifth assessment report was prepared, a large expert survey in which 90 sea level experts from around the world participated, and we asked them what their personal assessment was, how much sea level would rise. And 65% of these experts expected a larger sea level rise than the IPCC. So that's, again, an illustration that the IPCC projections tend to be relatively conservative. Now, past sea level rise was not uniform. I mentioned that. Future sea level rise will also not be globally uniform. There are various reasons for this. Two of the most important ones are shown here. In the top left, you see the effect of ice sheet melting. There's an interesting physical phenomenon there, that the ice sheets, they have a pretty large mass and therefore a large gravitational pull that noticeably pulls the seawater towards the ice sheets. And therefore, when the Greenland ice sheet, for example, loses mass, the ocean water will move away from the Greenland coast. And that's why in that top panel, you see around Greenland, you see this big white blob, which has kind of below zero sea level change, and a similar thing near Antarctica. And so paradoxically, when these ice sheets melt, along the coastlines of Greenland and Antarctica, sea level will actually drop. But it will rise all the more further away from the ice sheet. That's why in the tropical and subtropical regions here, you see these orange and red colors where you get a especially large sea level rise in response to ice sheet melting. Another reason, incidentally, since we're in Iceland, that is to the benefit of Iceland. As you can see in this map there, Iceland is in that white part of the response to continental ice sheet melting. So that helps to limit the sea level rise in Iceland to something lower than the global average. Now, in the bottom panel here, you see the effect of a slowdown of the Gulf Stream system, also technically known as the Atlantic overturning circulation. And that has the effect of leading to some additional sea level rise on the United States Atlantic coast. Cities like New York, like Boston, will be affected, especially by this when the Atlantic overturning circulation slows down, as the models project, and as we also think we are already observing now. And there actually has been a bit of excitement when the Atlantic overturning had a kind of brief weak phase in 2009, 2010. The measurements show a kind of temporary weakness there in the overturning that was associated with an incidence of particularly high sea levels on the US Atlantic coast. If you put the various factors together that lead to regional differences in sea level rise, you can take this diagram on the right-hand side from the IPCC, and it shows you that, for example, Iceland there is practically almost the best of any inhabited land area in terms of getting the least sea level rise, whereas the United States East Coast there is in the kind of dark red area where they get more than average, more than the global average of sea level rise. So if we want to put these future projections of sea level rise into a larger context of the last millennia, it looks like that. In comparison to that rise that we expect in future, the variations in the last millennia are really dwarfed, and sea level looks very stable in comparison to what will happen ahead of us in this century. Now, if we think of the longer term beyond the year 2100, then the two big ice sheets are the big players. They are the big gorillas in the room. They are very slow to wake up, but they are waking up now, and in the long run, that's where a lot of ice is. The Greenland ice sheet alone holds enough ice to raise global sea levels by 7 meters. From Antarctica, you can get another 60 meters. So when we came out of the last ice age and sea level rose 120 meters, that means 2/3 of the continental ice that was there at the time in the ice age was lost. We have 1/3 left, around about 60 meters worth or a bit more. And so we cannot afford to even lose a small percentage of this ice without drowning coastal cities and island nations. And this, by the way, this animation shows data from the GRACE satellite mission that measure the Greenland ice mass. And you can see on this diagram where the Greenland ice sheet has been losing mass in the last years. And that's obviously around the edges because the ice is thinner there and the elevation is lower. This ice sheet is about 3,000 meters thick. So in the center of the ice sheet, up there, it's high up in the atmosphere, it's very cold. Very rarely there's any melting up at this altitude. We've only seen a few days in the last decades where that has actually happened, some surface melting there. So overall, in the center of the ice sheet, it has been gaining some mass because of the additional snowfall that comes with global warming. You have more open water in the Arctic Ocean, you get more evaporation, and so you get additional snowfall. And because in the center it practically never melts, you gain mass, but at the edges you lose a lot more mass than you gain in the center. And the overall declining curve here shows the overall mass loss of the Greenland ice sheet. Now in Antarctica, we also observe a lot of mass loss, and there is also a special situation there with the marine ice sheet instability that is probably already occurring in Antarctica, in West Antarctica. This is an animation of NASA data of the ice flow, illustrating that the ice flow has sped up in recent years. And here you see the elevation change in that gray area that is covered by the data. And where it gets orange, as time progresses in this animation, you see that the ice sheet is losing altitude, so it's also losing mass there. And the dangerous thing with the West Antarctic ice sheet is that the entire ice sheet can become unstable if this so-called marine ice sheet instability kicks in. And there have been several studies in the last 2 years arguing quite strongly that this ice sheet instability has already been triggered, that we have passed the tipping point for West Antarctica, which will lead to the complete loss of the West Antarctic ice sheet. That alone would add about 3 meters to global sea level rise. Thankfully, this will take many centuries to play out, so this doesn't mean that we have to greatly increase our projections for this century, because that is, again, it's a slow process, but it means that we are committed to a very long-term sea level rise due to destabilizing that ice sheet. And this is, I think, an important way how we have to think about sea level rise. We have to think about how much future sea level rise we commit the world, our ancestors, by the actions that we take during the next few decades. Because we are triggering, and in fact have already triggered, a very long-term process of sea level rise. And just very recently, a new study has been published showing the long-term consequences of global warming for these 4 different scenarios that you see playing out on the top right there. And if we look at even the most optimistic scenario with the least global warming here, that ultimately ends up with about 25 meters global sea level rise. And you can imagine that this wouldn't leave many coastal cities that we have now standing. And as you see, this is over a very long time scale, but it is something that we are causing today by our emissions. So finally, I want to say a few words about the consequences, the impact of sea level rise. And one of the first ones that we feel is that the frequency of extreme sea level, or you could call it storm surges or flooding events, is going up with sea level rise. And this is for a medium global warming scenario here from the IPCC report, showing by what factor the frequency of flooding events along different coastal sites here goes up. And even though this is by 2100 and it's a medium scenario, it's not some really extreme amount of sea level rise, but all these kind of orange and red dots have an increase in the frequency of flooding by a factor of 100 or 1,000. So you get 100 times more often that you exceed a certain flooding level in your city there. And that, even to me as a scientist who is studying sea level, initially was quite surprising by what huge factor the flooding occurrences go up just from a moderate amount of sea level rise. And this kind of flooding events that can look like this, I took this photo in Venice a few years ago where Piazza San Marco is flooded quite regularly, some winters more than 10, 15 times. And that is to do with the fact that, of course, as we all know, Venice is a very low-lying city, but also Venice has experienced an above-average relative sea level rise, not just those 20 centimeters global mean rise, but about 70 centimeters in the last few centuries, partly because of the weight of these heavy buildings that have been built in Venice on uncompacted sediments. So, and also partly because of groundwater removal by industry on the mainland of Venice. And that's why Venice is like a kind of canary in the coal mine. It's an early warning of the kind of future that other coastal cities will experience later on as sea level rise progresses further during the course of this century. And small island nations are, of course, at the forefront of the impacts of sea level rise. And if you look at this picture here of Malé, the capital of the Maldives, you can see there is very little adaptation opportunity here in such a place to protect yourself from sea level rise. And the Maldives, in fact, are now already in the process of building an entire new island that is raised higher above sea level, and they want to relocate a large part of the population to this new artificial island. They are lucky in the sense that they can do that because of the shallow waters around there. Another place that has no such option is Bangladesh. You can see here that a large part of Bangladesh with very large population is very close to sea level, and Bangladesh has already in the past experienced devastating storm surge events because they're also in the path of tropical cyclones, and it's one of the poster childs of high-risk area from sea level rise. So with that, I want to come to the end, and I think I've shown to you that sea levels are rising in response to global warming. It's a very simple, logical, physical response to warming. The 20th century rise is unprecedented in the last millennia from the Proxy data that we have from along the world's coastlines based on salt marshes. This rise will accelerate. We can kind of prevent most of the acceleration by limiting global warming below 2 degrees. It's one of the good reasons to actually do that. If we don't implement the Paris Agreement and let global warming just run unabated, then we can expect up to 1 meter sea level rise by 2100. But in the longer term, if you look several centuries into the future, there will be a much larger rise of several meters. Thank you very much.